Most of us are familiar with the basic concept of a function from high school algebra class. There is some dependent variable y defined by an independent variable x. In this case, y equals sine x. Sometimes this notation is used interchangeably. You have some function f of x defined by the independent variable x. Hopefully this looks familiar so far. Consider the column of numbers on the very left, 0, 0.2, 0.4, etc. X is the input variable, so we plug a number x into the function and it should output a unique y value for each one. On a scientific calculator, we would have to push the button boxed in red to get the sign of any number x. That's the straightforward way of doing things. If you're curious of the algorithms behind how sine x is actually computed, I have other lessons on trigonometry, Taylor series, and interpolation. So after pushing the button on your calculator for each x input, we get all the y outputs in the second column. One number for the input, one number for the output. Simple enough. Finally, we can plot each x and y coordinate on a graph like the one seen here. The x-axis runs horizontally and the y-axis runs vertically. I'm not going to belabor you with too many details here because this should all be reviewed from high school algebra. Now we can start talking about implicitly defined functions. In contrast, the functions we were just talking about are sometimes called explicit functions. X and y were separated. Y was on the left-hand side, and all the x's were on the right-hand side. Implicitly defined functions have all the x's and y's mixed together, as seen in the example in the last line. Sometimes we can separate them out, and sometimes not. In this case, we can separate them. How so, you might ask? Consider plugging in a single x value, like x equals 0.2, seen in purple. That leaves us with 3y squared minus 6y plus 5.92 is all equal to 0. Before we plugged in a number for x and got a single number for y. Now we plug in a number for x and get a function for y, an infinite number of values for y. It may not seem like we're going anywhere, but notice the coefficients in red, green, and blue. Those are coefficients for a quadratic equation, with the variable being y. Here is a brief reminder of the quadratic formula. This should have been covered in high school algebra class as well. We use it to solve for the variable t, in this general case, or y in our specific problem. If you want to know more about this, check out my other videos on that topic, because it is time to move on. Instead of plugging in x equals 0.2, or any other specific number, let's keep it as a variable and still solve for y. After some rearrangement, notice in the last line that we still have a quadratic equation a times y squared plus b times y plus c. The only difference is that each coefficient is now a function of x instead of a constant number. Once again, here's another quick reminder of the quadratic formula we are going to use in order to solve for y. All I'm going to do is plug in the red, green, and blue expressions from the previous screen for a, b, and c. So I plug those in and do a bit of algebra. Pause the video and follow along at your own pace if you so desire. The final result is in the last line. Y is now a function of x. Y on the left-hand side and all the x's on the right-hand side. We have transformed an implicitly defined function into an explicit function. Remember that explicit functions are easy to plot because we plug in a single x value and they spit out a single value for y. Before I show you the plot, notice the plus or minus symbol. This indicates we're going to have an upper branch and a lower branch. That is seen here. The blue is the upper branch corresponding to the plus sign. The orange is the lower branch corresponding to the minus sign. They join together at the rightmost and leftmost points of the graph. Thus, each branch can pass the vertical line test for a function. So why is that gray line there? Just as a side note for now, This implicitly defined function happens to be an ellipse. It is a circle that has been flattened, translated rightward, and then rotated 45 degrees about the origin. There is a way to show this algebraically for any angle, but the topic of rotations will have to be reserved for another lesson, if popular interest demands it. Using the quadratic formula, I could follow the same process to explicitly define x as a function of y, x on the left-hand side, all the y's on the right-hand side. Because of the unique symmetry of this problem, the end result basically swaps out the x's and y's. So now we plug in a single y value, and the function spits out a single x value. By definition, this is the inverse function. Sometimes inverse functions are difficult or even impossible to define explicitly. That also is a separate topic, so I mention it in passing only. The plot of that is seen here. We still have two branches for the plus and minus. Overall, it covers the same set of coordinates, except we have a left branch and a right branch. They are joined at the topmost and bottommost points of the curve. Hopefully by now you understand the differences between an explicit function and an implicitly defined function. In this case, we were able to separate the x's and y's. This is not always the case, unfortunately. In the next lesson, we will see an implicitly defined function that cannot be transformed into an explicit one. All the x's and y's are still mixed up. So how are we supposed to graph that? Stay tuned to find out.